I'm here today to show you the new perceptual rub buzz algorithm in Soundcheck 20. Let's start with why we developed this. In short, we made this to help manufacturers attain higher yields and greater profitability while still shipping quality products. This has become increasingly important in the past decade or so. As we all know, profit margins are very tight on high-volume, low-cost products, such as the small speakers used in phones, headphones, smart speakers, and other voice-activated devices. So what is rub buzz, and how does a perceptual metric increase yields? Rub buzz is a descriptive term for audible, high-order harmonic distortion. It's caused by manufacturing problems such as rubbing voice coils, improperly glued parts, for example, spiders and cone surrounds, or too short or too long voice coil lead wires. Rub buzz defects sound harsh to the human ear, so allowing products with these defects to ship can damage your brand's reputation for quality. For this reason, rub buzz is a critical end-of-line QC measurement. Conventional rub buzz detection methods have been around for years and work well. If you make a quality product, you're probably already measuring this on the production line. However, these methods detect all rub buzz faults, whether they're audible or not. This is great in terms of understanding what's going on with your production line, but since not all rub buzz faults are audible, either due to their frequency or masking by other frequencies, you may often reject product that actually sounds just fine. Perceptual rub buzz metrics enable you to identify only audible faults in your products. If you can identify and remove only those products that sound bad, rather than all those with harmonic distortion, you can improve yield with no negative impact to your customers. Perceptual metrics use a combination of psychoacoustic models and other measurement techniques to arrive at a single number for distortion loudness in fawns. You may be thinking to yourself that perceptual measurements are not new. That's true. We launched the first perceptual distortion metric over 10 years ago, back in 2011. And this past year or two, other manufacturers have launched similar algorithms. However, all these existing algorithms suffer repeatability issues and sensitivity to background noises, which has hampered their widespread adoption on the production line. What we're introducing now overcomes these issues, and we believe it's the first perceptual rub buzz metric that is truly suitable for a wide range of manufacturing environments. I'm going to start off with showing you some results to demonstrate what I mean. Then we'll go into some deeper details about the algorithm itself. In order to demonstrate this clearly, I have selected 3 speakers of an identical make and model. One is a good unit with no audible distortion. The second features mild or just audible distortion. And the third displays quite harsh audible distortion. Now let's look at how they measure with the original 2011 algorithm. For this test, each speaker was measured 10 times and the individual results plotted. As you can see, distortion level accurately reflects listener perception. The bad unit, the red line, shows the highest level. The borderline unit, the orange line, shows some distortion, but clearly lower than the bad unit. And the good unit, the green line, shows no audible distortion. However, you can also see that there is significant variation in the results each time a speaker was remeasured. This is primarily due to background noise. In a production environment where there's only one test sweep on each device, this variation makes setting limits challenging. Let me just explain in more detail why this is a problem on a production line. In a lab, we've taken 10 results and the trends between speakers are obvious. But on the production line, you get just one sweep. Let's say our golden unit gives us this result. We set limits based around it. Then we measure our speaker and it passes. Now let's say the conditions were marginally different when we measured it and we get this result, and it would fail. You can't afford to have this type of inconsistency on a production line. So this is why repeatability and immunity to background noise is such a big issue. Now let's look at the results with our new 2021 Enhanced Rub Buzz metric. Also, with the exact same 10 measurements for each speaker, you can see here a hugely improved correlation between the 10 results, as you would expect with less sensitivity to noise. This improved repeatability makes it considerably more reliable than the original algorithm and much easier to set limits. This may look like a small detail, but it's actually hugely significant in terms of the usefulness of any perceptual distortion measurement. This new algorithm isn't just about noise rejection. We've also enhanced the part of the algorithm that replicates the human ear's behavior for greater accuracy. It now reveals increased detail in the ear's highly sensitive 1 to 5 kHz range, more accurately mirroring human perception. We'll talk a little more about this later. So to summarize, the new algorithm offers both better correlation to human hearing and is much more repeatable, which makes a huge difference to its potential for production line perceptual evaluation. For comparison here, I'm going to show you one more graph. This is a perceptual rub buzz algorithm recently launched by another test and measurement company. You can see that it demonstrates similar repeatability problems to Soundcheck's original 2011 algorithm. And interestingly, it measures greater audible distortion at low frequencies for the speaker that was subjectively assessed as borderline than the bad one. We can validate the results of the Soundcheck algorithm not only by comparing them to listener perception, but also by comparing them to higher order harmonic analysis. Part of the challenge with these listener evaluations of these faults is that it's hard for the untrained ear to differentiate these faults, particularly with the fast sweep stimuli that we use for end-of-line test. I'm going to play some test signals for you to hear, but bear in mind that unless you are trained in listening to rub buzz distortion, you may find it hard to tell the difference. Also, you're listening to the signal with your own speakers transmitted over the internet, so the fidelity is questionable. We'll make these files available on our website so we can take a closer listen. Anyway, in order to simplify both the listening experience and visualize measurement results, I'm going to use a fixed frequency near resonance at 256 Hz, which causes maximum cone displacement. This frequency is where both the bad and the borderline speaker exhibit a peak in the perceptual distortion, so it should be easier to hear than a rapid sweep stimulus. I'm also going to show you the resulting distortion spectra for all three speakers. So even if you can't hear the difference, you can see the harmonic distortion for all three speakers. So first, here's the good speaker. And here's the bad speaker. One more time. Good speaker. Bad speaker. Could you hear the difference? And now for the borderline speaker. It does have measurable perceptual rub buzz, but not as bad as the bad speaker. One more time. Here's the good one, again, as a reference. Now let's take a look at the distortion spectra. Bear in mind that this is conventional rub buzz, so it shows all harmonics, audible or not. You can clearly see that there are minimal high-order harmonics for the good loudspeaker, the green line, which correlates well with the perceptual measurement, as you would expect. Both the bad and borderline speakers show elevated high-order harmonics, and again, in line with Listen's perceptual algorithm. The bad one, the red line, clearly has more high-order harmonic distortion than the borderline one. At no point does the borderline speaker, the orange line, exhibit more rub and buzz. As one would expect, the perceptual distortion algorithm amplifies the relative magnitude of the distortion in the highly sensitive region of human hearing. Now, I'm not sure if you noticed that the other perceptual algorithm I just showed you, the one that is not a listen product, reveals little difference in the maximum distortion audibility of the two speakers with rub and buzz, even though human listeners perceived a significant difference in distortion level. Now, I'm not sure if you could hear the difference, but even if you couldn't, you can clearly see from the measurement that the harmonics are considerably higher throughout the frequency range in the bad loudspeaker. In fact, at the 256 Hz we just listened to, that algorithm actually showed greater distortion with the borderline speaker, the orange line, than the bad speaker, the red line. This doesn't correlate at all with either the high order harmonic distortion measurement or listener perception. So that's what we have for results. Now I'm going to hand over to our DSP engineer, Rahul, who will explain some details about the development of this algorithm.
Hi, I'm Rahul Shakya, DSP engineer at Listen, and I'm going to explain a little about how this algorithm works. Back in 2011, we launched our first perceptual algorithm, and the fundamentals of that remain in the new algorithm. However, we have made sweeping changes in the underlying perceptual model to improve correlation with listener perception, and we have also implemented proprietary noise reduction techniques throughout the algorithm. There's years of research, a lot of psychoacoustics, and a huge amount of math behind this straightforward metric. I'm going to simplify it to the basic building blocks in order to explain how it works in a more accessible way. We start off with a stepped sine sweep test stimulus and capture the response spectrum. A novel noise reduction technique minimizes the effects of background noise. The signal is then processed in two separate paths and combined at the end by an overall response metric. On the left-hand side is our perceptual filtering algorithm. This models the frequency response of the ear. Our model is based on the sound psychoacoustic principles outlined in the ITU peak standard, which includes a basic model of the human auditory process. It also includes additional proprietary methods which improve the correlation with subjective listening tests. Let's take a look at what's going on. In each frequency step, auditory filter bands convert the FFT spectrum to a bark scale to replicate ear filtering. Next, an ear weighting filter compensates for the transfer function of the outer to inner ear, and finally, the internal noise of the ear is added. Next, a frequency spreading function is applied. This is a simplified mathematical representation of auditory masking curves that mimic the psychoacoustic filters of the ear. These masking curves change with frequency and level. The fundamental and its masking effects are then removed to give the audible distortion of the speaker plus noise. This is summed over the frequency range to give the perceptual noise loudness for a single tone of the input signal. On the other branch of the algorithm, the harmonic structure of the response is quantified using the power capstone. A strong and extended harmonic structure is a signature of rub and buzz. In the final step, the result of the harmonic analysis is combined with perceptual distortion to accentuate the rub and buzz and return a harmonically weighted value for rub and buzz loudness in fonts. If you've been following us for a few years, you might be wondering, how is this different from what we launched back in 2011? The answer is that although the overall principles are the same, there are two significant changes. First, the perceptual filtering algorithm in this left branch is completely different. Although it relies on the same basic principles from the peak standard, this is now enhanced with proprietary techniques to improve correlation with human hearing. This makes it more accurate, especially at frequencies where the ear is very sensitive. Second, a new proprietary noise reduction algorithm offers significantly improved repeatability, which makes limit setting easier and makes the measurement a viable option for production environments. You can see here we compare measurements on the same speaker using both the original perceptual rub and buzz metric and the new enhanced version. You can see that the new algorithm shows much greater distortion in the mid-frequency range. This reflects the enhancements to the perceptual algorithm that brings it closer to the behavior of the human ear. Many speakers were subjectively and objectively tested during the design of this algorithm, and the correlation with subjective scoring was significantly higher than with the prior version. Hopefully that explains the algorithm clearly. Now I'm going to hand back to Steve, and he's going to talk about how the perceptual distortion fits with other production line metrics.
Thank you, Rahul. So we've demonstrated results and explained how it works. I just want to finish up by putting this into context with other end-of-line distortion measurements. You may have already measured conventional rub and buzz and loose particles, and this measurement sits right alongside them. Because it uses the same step sign sweep stimulus, it can actually be measured simultaneously with no increase in test time. You may be wondering why you would need to also make other end-of-line distortion measurements if you have this. So let's dig a little deeper into that. If all that you want to know is whether audible rub and buzz distortion is present, then this measurement alone should be enough. However, if your goal is maximizing yield and profitability from your line, then you should measure 3 different types of distortion: perceptual rub and buzz, normalized rub and buzz distortion, and loose particles. Here's why. Perceptual rub and buzz can be considered the should I ship it metric. If the device passes this, even though it fails conventional rub and buzz, the defects are inaudible, so will not affect customer perception. Basing pass-fail decisions on this, rather than conventional rub and buzz metrics, can increase yield. Traditional rub and buzz measures all incidences of high-order harmonic distortion, whether audible or not, and is a great metric for understanding the distortion you might be hearing. Soundcheck's normalized rub and buzz measurement is more accurate than other conventional methods because it normalizes the result to remove the effect of the frequency response. It is also fast because it measures all harmonics simultaneously and independently. Looking at the exact harmonics reveals much about the cause of the distortion. For example, even order harmonics are an indication of an asymmetrical nonlinearity, such as the voice coil not being centered in the magnetic gap. Odd order harmonics are an indication of a symmetrical nonlinearity, such as clipping or reaching speaker cone and spider excursion limits. High levels of harmonic distortion in the 10th through 15th order range usually indicate a rubbing voice coil. Distortion at the 50th harmonic and above is frequently caused by voice coil lead wires hitting the cone. Careful selection of the harmonics you analyze can reveal many manufacturing defects and enable early correction of production line issues before waste occurs. Trends can also be monitored over time so that production line adjustments can be made if something is drifting out of specification. And let's not forget loose particles. Loose particles are caused when foreign particles such as glue or magnet fragments become trapped in the gap behind the diaphragm or dust cap during the manufacturing process. The random clicking, popping, or rattling noises made by these trapped particles cause transient rather than periodic distortion. This means that they're not identified using the same methods as rub and buzz, but rather by using time envelope analysis of the waveform. Like conventional rub and buzz, this is a valuable metric for identifying where problems are occurring on the production line before they become serious enough to cause audible defects. So in an ideal world, you'd measure all 3 distortion metrics at the end of your production line. The good news is that these 3 measurements, plus other end-of-line metrics such as frequency response, THD, polarity, and impedance, can all be measured with a single sign sweep, ensuring that rapid throughput is maintained. So that's it for me. Hopefully you now have a good understanding of our latest perceptual distortion metric and are ready to try it out for yourself. This algorithm is included in all Soundcheck 20 packages at no additional cost. If you have a support contract with us, You'll be able to use it as soon as you download the latest version. And if you don't have SoundCheck already and want to try the new ePRB algorithm, please contact your sales engineer or local rep.